All right, hello everybody. Welcome to another week. Don't forget, this week you have an exam. In the first 5 chapters, including this chapter. So we want to go through this and make sure you understand everything. Don't forget, in your textbook, there are plenty of problems to work on. So just work on those problems, make sure you're ready to go. Today, we're going to talk about doing a research hypothesis. Well, it's all part of being a researcher because we ask a lot of questions as researchers. And from those questions, if we are scientifically minded, we form hypotheses. We often don't get an opportunity to test our hypotheses. Sometimes people just make assumptions based on observations, but that's not enough. We actually have to do research in order to find support or to disconfirm our hypotheses. So generally, the process is you ask a research question, you formulate a hypothesis, or you can do more than one hypothesis. You select your alpha. We'll talk about all this stuff. Select the appropriate test statistic and calculate your test statistic value. Draw your conclusion and then repeat with a different sample. So you're supposed to be doing this over and over again until you get some kind of a conclusion, either that my hypothesis is wrong or that it's correct and has support. So a research question is a very, very detailed question and includes what are called operational definitions. We operationalize variables so we can operate on them. Here's a textbook example from my text. Is not like, you know what I mean, my textbook. Danielsville High School students. Okay, so that's my sample and population, right? So the RWI statewide population mean is 50 with a standard deviation of 30. Our sample from Danielsville High School had a mean of 70. Our research question is, do Danielsville High School students weigh more on average than high school students statewide? So I guess what I want to know is, do my students constitute a separate population from the statewide population? That's in terms of weight using the RWI, that weight index. My hypotheses are, well, I have a null and an alternative. To be clear, when we do research in journals or write grants, we generally don't write out our null hypothesis, it's assumed. We focus on our research hypothesis, also known as our alternative hypothesis. But in stats, we need to acknowledge our null. So our null hypothesis is the hypothesis we want to reject. And generally said there's no effect at all. So it could be no effect of a treatment, or there's no difference between two populations. So in my case, I would say that, that my sample doesn't differ from the population in terms of the RWI. So let's take a look at this, the way I wrote it out. And notice that I have this H symbol that stands for hypothesis. And a 0 here stands for null, or the hypothesis I'd like to nullify, actually. I say that my sample mean is equal to the population mean. That's my null hypothesis. We always start with the assumption that we are incorrect. This is part of null hypothesis significance testing. The onus is on the researcher to find support for the hypothesis. I could also write this as the difference between the sample and the population mean is equal to 0. Either way, we have the same thing. My alternative, well, in this case, the population mean was 50, right? So, right, 50 with standard deviation of 30. So that's why my null hypothesis is that my sample mean is equal to 50. My alternative hypothesis, I can either write that as H1 or HA. You'll see it done both ways, depending on where you're at and with whose book you're reading or whose papers you're reading, if they include them. This is our research hypothesis, or our wished for hypothesis. If we were to write out this hypothesis symbolically, we'd write out something like this. Well, our alternative hypothesis has to, of course, match what our real interest is. So we were wondering if our sample weighs more on average than the population, right? We already have a sample mean of 70, so clearly 70 is larger than 30, but we're not interested in just if it's different, but if we were to look at all possible samples from this population statewide, is our sample far enough from the population mean for us to say that it's truly, truly different. It constitutes a different population of individuals, and that's what we're really looking to do. So my alternative hypothesis is that the sample mean is greater than the population mean. So in this case, it would be sample mean is greater than 50. And we can talk about other types of alternative hypotheses, and we will shortly. In any research study, there are 4 different outcome possibilities in terms of hypothesis testing and the decisions we make. So there's a true state for the null hypothesis. Either the null hypothesis is true or the null hypothesis is false. Then we make decisions. Either we reject the null or we accept. Some people say fail to reject. It's fine. Fail to reject, accept. I mean, if you fail to reject, you tend to accept it. So if I were to reject the null hypothesis and the null hypothesis is true, I would be committing what's known as a type 1 error. And that's what our alpha is. So remember, I mentioned alpha earlier. Alpha is the probability of a false positive result. So that's false positive, right? I reject the null when I shouldn't have. That's false positive. That's what our goal is, to hopefully reject the null. In most cases, there are some cases where we don't. If the null hypothesis is false and I reject the null, that's exactly what I want to do, right? And the probability of this occurring is what we call power. So power is the probability of rejecting a false null hypothesis. You'll see also 1 minus beta, but I didn't explain what beta is yet, and you'll see it in a second. Let's say the null hypothesis is true and we accept it. Well, we're confident in that case, right? Confident that our sample belongs to that null population, whatever the population was that we're comparing our sample to. If the null hypothesis is false, but we fail to reject it, accepting the null when it's false is failing to reject it, we consider that a type 2 error, and that's known as beta. So now we can say beta and power are inversely related, or they're complementary, I should say. So power is 1 minus beta, and beta is 1 minus power. So whatever your power is, if you want beta, subtract power from 1, and the other way around as well. Okay, let's get to know these symbols. Beta is type 2 error, alpha is type 1 error, power is 1 minus beta, and then confidence. Well, we'll talk about confidence. I think we did it last week, right? The confidence intervals. There is an ideal power in most research is greater than or equal to 0.80. Well, you should be saying, well, why shouldn't it be 1? Shouldn't we want to be 100% certain that we rejected a false null hypothesis? Well, one of the problems with that is that sample size, with larger sample sizes, we may be rejecting null hypotheses that are, I mean, they're inconsequential, right? If we say a treatment reduced weight by, say, 20 pounds in a person who's morbidly obese, that'd probably be a good thing, right, to start. If I have a really, really large sample size, because of the impact of sample size and power, I may actually reject a 1 pound change for a treatment. And while that is statistically significant, it's not practically meaningful. So we try to limit what our power is so we don't get overpowered or we start rejecting everything. There's ways we can deal with that if we need to, but we can talk about that later. So as I mentioned, power is affected by sample size. So selecting our alpha is our probability of a false positive result. We have to look at our distribution to understand why we make the choices that we do. This is our null population here. We look at the probability of our observed result from our sample, like we were comparing our sample of 70 versus 50. The greater the difference between our sample mean and the population mean, the less likely is this population to occur by, the sample to occur by chance alone. So it's more likely to be a truly meaningful result. But if we look at this distribution here, this represents 100% of all possible values within the population, and we draw our samples from this population. Some samples are going to be, I think I showed you this last week when we talked about distributions. Some samples are going to be closer to the mean and some samples are going to be further and further away from the mean. What constitutes far away enough for us to consider something being significantly different? Well, one thing we know is that values to the right here past whatever this statistical value is, and we'll talk about z's in a second. Standardized value is 1.645. This is 1.645 standard deviations away from the mean of 0. So a value this large or larger has only a 5% chance of occurring if this null hypothesis is true. So if we were to reject the null hypothesis and we're somewhere in here, but we falsely rejected the null hypothesis, our probability of being wrong is very, very small, because any value in here has 5% chance or less of occurring if the null hypothesis is true. What do I mean by doing a false result? Well, let's say we're comparing people in terms of happiness, right? We believe we have the happiest group of people in the world. And on this one day, we well, you know, like in the last, say, month or so, people have been exceedingly happy. So, wow, they must be different from the population as a whole. So the population mean value and happiness, and then our sample falls out here. Well, it turns out that the only reason they were happy was because their favorite team is winning all the time, right? So that's a false conclusion to conclude that they are happier, like they constitute a population of happier people than the population as a whole. Right, just because they were happy, you know, on this date when we collected the data, it wasn't a real difference. It was based on the way the team was performing at that time. Had the team been losing, the difference would have been either 0 or even could have been negative. They were less happy, right? So the thing is that we want to be sure that we have a difference that is truly significant. So the further and further away our cutoff point, what our cutoff point is based on our alpha, our probability of a false positive result, the further and further away we are, the less likely is this to be a chance finding. Like if somebody was, a sample had people this happy, even though the team is winning, they're still so far away that, you know, gee, the likelihood of a result that far or further from the mean is really, really small. So probably are happier people, even though their team is winning, but they probably are happier, right? So that's why we do what we do. So we pick our level of alpha depending on the situation. It depends on what's at stake. Most people use a 5% chance of a false positive result. That's this purple area. This is the upper 5% of the distribution. But sometimes we'll choose a smaller area, like alpha equals 0.01. We do that when we have to be really careful about a false positive result. Like, for instance, if we're testing a drug that treats some disease but has serious side effects, we want to be really, really sure that we're right. So instead of alpha of 0.05, we move our critical value from 1.645 to something higher, right up here, right? I'm not really sure what the z value is associated with an alpha of 0.01, but it's going to be up here somewhere, okay? The upper 1% of the population. By the way, these are complementary. So like if this alpha here is the upper 5%, the remaining area is the lower 95%, right? Okay. So we can sometimes use an alpha that's even larger, like 0.10. Some people even suggest 0.15, but those are for situations where we're testing something for the first time and there's really nothing at risk. I wouldn't have an alpha of 10% or 15%, accepting a 10 to 15% of a false positive result if I was testing a drug. But I might do it if I'm testing a new program just to see if there's any potential for it and there's no possible harm, right? See if there's any potential for it for the future. So our choice of alpha is our choice. There is no alpha written in stone, but there are popular values. 5% is the most popular. The other two are 0.01 and is probably more popular because it's more stringent. than 0.10, and then 0.15 has been suggested by one author, but you'd have to make a good case. Anytime you choose something, you always have to justify it. So you'd have to be able to justify it. We saw the z-values already, but z-values are test statistics that we use when we're comparing a sample to the population. And what's really important, we have the population standard deviation. So this is very useful in very specific situations, like if we're comparing somebody to some standardized test result where we have the mean and the standard deviation. Usually you have those in standardized tests where we have all the data, the entire population of values. So let's look at our example data on 33 Danielsville High School students who completed the RWI. Their mean was 70. That's what we were doing before, right? So our research question is, do Danielsville High School students weigh more on average as measured by the RWI than high school students statewide? So it's very precise, right? This research question, right? I say based on the R, that's what I mean by precise. It mentioned exactly which measure we're using. Right? So very, very precise. The null and the alternative hypothesis, and I notice I say verbally, because you do need to explain things to people, not just in symbols. Most people don't understand symbols. You always have to be able to convert back and forth. The null hypothesis is the sample mean equals the population mean, or the difference between the sample and population mean is 0. The alternative hypothesis is that the sample mean is greater than the population mean. So here's our null, and here's our alternative. We select an alpha of 0.05. We accept, meaning we accept no more than a 5% chance of a false positive result. So we have the population standard deviation, so we can use our z equation and conduct a z-test. We have sample mean is 70 minus population mean divided by the population standard deviation, which was 30. This denominator is a quotient where we have 30 divided by the square root of the sample size. So because the sample size is in the denominator, the larger the sample size, the smaller this quotient. The smaller this quotient, the larger the z-value. The larger the z-value, you'll see the more likely you are to reject the false null hypothesis. So we get 3.830. If we didn't have the population standard deviation, we use the sample standard deviation, which is, as you know, is an unbiased measure of the population standard deviation, or estimate of the population standard deviation. And then we want to test whether or not we have a significant difference. So the question is, how far is our calculated z-value from the population mean? So we're going to do everything in this standardized world now, right? So no longer are we interested in 70 and 50. I mean, we are, but we're looking at the difference, and the standardized difference is 3.830. So we're going to look to see how far away 3.830 is from the population mean. And the way we're going to do that is we're going to look at probabilities. So we're going to ask, what's the probability of a value of 3.830 or greater given the null hypothesis is true? And that's what we ask here. What's the probability that z is greater than or equal to 3.830? So that's what we want to know. So what's the probability of a value this large or larger given the null hypothesis is true? Now, to do that, we're going to go to the appendix of your book here. And this is a z-table. And the z-table has, where's my little cursor? There it is, okay. The z-table is, it's just like the distribution I showed you moments ago. It's centered at 0, so it has a mean of 0, and then all the values to the right or left are standard deviations away from the mean. This table, it only shows you, this is really important, it only shows you the difference between the mean and your z-value to the right. So these are all going to be positive values. If it showed you values to the left, they'd be negative. But because this distribution is symmetrical, everything you see to the right is equal to everything you would see to the left. So the difference between 0 to z is the same as the difference from 0 to negative z. The purple area represents the area under the curve that's highlighted. So this is the area, right? Okay. So the question is, well, and also everything goes from left to right, from left to right. I can't see my little cursor for some reason. Everything goes from left to right in this figure, okay? Left to right. All right. So that A that we're looking at in the figure is going from left to right, the area. We talk like what's the probability of being, greater than 0. So that's, we're moving from left to right. As our Z value increases, so should our area. All right, let's go over here. I can't see my cursor. Oh, there it is. Cursor is very small for some reason. All right, so what you see inside this cell is areas. These are these areas representing A. The Z value we read as such. So this is Z of 0.0. So this is right at the mean. 0.00. So notice how there's 2 decimal places here. There's only 1 here. So this adds that second decimal place. So this is 0.00. 0.00. 0.10. 0.10. 0.11, right? Here, 0.12, and so on. This is a Z value of 1.00. A Z value of 1.00 encompasses 34.13% of the area. If you multiply this by 100, get 34.13. That means the area between 0 and a Z value of 1 represents 34.13% of the population. We should know that because we did the empirical rule, and that's what we mentioned. So a value of 1.64, 1.60, 1, 2, 3, 4. This is a value of 1.64. It represents basically 45% of the population, right? So 45% of the population is between 0 and 1.64. So a Z of 1.64. All right. If I wanted to know what proportion of the population is below a Z value of 1.64, this is really important. Now listen closely. I don't just look at this area because it's this area here plus everything below it, because everything's always moving from left to right as we accumulate area, right, under the curve. So what's the probability that somebody has a Z value less than or equal to 1.645? It will be this 45% here plus the 50% would be 95%. But our question is, if you know from what I showed you in the null hypothesis, what's the probability of a Z value greater than or equal to, I think we were at 3.83, right? At 3.830, 3.830 greater than or equal to 3.830. So that would be 1 minus the probability of being less than 3.830, right? Because we know that rule of complementary events. So we need to find a Z value of 3.830 here, right? Well, I don't have one, right? The largest value in this table is 3.5. 3.50, 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, so a value that large or larger is going to be at least higher. Listen to me closely here. At least higher than 49.98. 49.98. So the Z value somewhere here. The area between 0 and my point. It's going to be at least greater than 49. What did I say? 49.98, right? 49.98, and then I have to add the other 50%. So it's going to be greater than at least 99.98, right, percent of all values. But the question isn't what percentage of individuals are at or below. We're not talking about we're not talking about one's percentile. We're asking what's the probability of a value greater than or equal to that value, right? 3.8 30. So let's go back here. So it's going to be 1 minus that 0.9998. So it's going to be somewhere less than 0.0002. All right, so I need you to study this and make sure you understand that there's plenty of examples in the textbook you can look at. So a probability of a z-value this large or larger, if the null hypothesis is true, is less than 0.002. Okay. That's a pretty big difference. So that means these kids definitely weigh more than the population. That's such a it's so far away that it's really unlikely for this to be a chance finding. Okay. It's really, really unlikely for that to be a chance finding. So they probably constitute a different sample of heavier individuals. Okay. And then the last thing you want to do is you want to repeat this study with other samples. So that sample could be just accidentally different for some reason. I mean, with weight, it's kind of an odd question, but perhaps the kids in that area were eating a lot of hoagies or something, or depending where you're at, hoagies or subs or what else, poor boys, and all these different terms people use for these kind of sandwiches. So it's possible that they were just eating a lot that week for some reason. Like there was an accident on the highway, dropped a load of hoagies, and everybody was eating up, and they just gained weight. So for that week, so it could be an accidental finding, but because that's such a large difference, it's unlikely to be accidental. All right, so that's it for this, and study hard and do the work in the book. Do the work in the book. All right, thank you very much.